it goes to 0, right? You can see it right there. So this, as x approaches infinity, sine of x over x is equal to 0. So now there are 2 to memorize.
If it went to negative infinity, it would
Same, yeah. Right? So we have that one to memorize, and we already memorized this one. So if you just remember what the graph looks like, that, you know, like there's like a little bell peak in the middle and then it levels off, it'll be easier for you to visualize. All right, so to evaluate limits at infinity, okay, let's just talk about what happens at infinity. So take a look at this first function. You have x squared plus 1, right? Now, when x is 1, right, you have 1 plus 1, and the x squared and the 1, they count equally, right? When x is 1,000, now you have 1,000 squared. Think about how many zeros that is. How many zeros is that? The 6 zeros, okay? And then you have a plus 1. Do the x squared and the 1 count equally now? Not even, okay? The x squared is way more powerful than the 1, all right? So for all intents and purposes, we can ignore that little itty bitty 1, okay? And the only thing that matters is the x squared, the term with the highest degree, okay? And on the bottom, it's going to be the same, the term with the highest degree. In this case, it's only an x cubed. Okay, you remember that, right? Yeah. So this is the limit as x approaches infinity. X squared over x cubed is what over what when they simplify? 1 over x, right? Because the x squared cancels and you have 1x left on the bottom. So now let's think about this. As x becomes infinitely large, right? What happens to 1 over x? It gets smaller and smaller to 0. So this is 0. So remember, when you have an x left over in the bottom, that the limit is going to be 0. Yeah.
anything get smaller to reduce.
Well, but if it was x over 1, right? If it was the limit as x approaches infinity of x over 1, and if x was getting infinitely large, it would just be like infinitely large. Yes, correct. All right, so take a look at this one. Again, we're only going to take the term with the highest power and the term with the highest power. So when the exponents are equal to each other, all we look at are the coefficients, okay? So exponents are equal. Look at coefficients. So this is just 3 over 2. That's it, huh? I know, right? Now, this one is a little bit different, so we have to do a little bit of math here. So this is the limit as x approaches infinity. It's always a good idea when you have multiple terms on top and one term on the bottom to split up the fraction so you have like a term, a denominator for each term. So this is going to be 3x over x plus the limit as x approaches infinity sine of x over x. All right, does everybody see what I did? I gave a denominator to the 3x and a denominator to the sine x. So now, what am I going to get from that first one, 3x over x? Just 3. Plus, what am I going to get for that one? 1 or 0? 0, because it goes to infinity. Okay? So, it's just 3, huh? Okay, yeah. No, it wouldn't work for this because of the sine x over x. So like if the sine x over x had other coefficients, then it wouldn't work. Alrighty, yeah.
So the limit as x approaches 0 of sine x over x is 1.
Yes.
Infinity is
0. Okay, yes.
Why is 3 plus 0? Wouldn't it be 3? Oh, no.
Okay. All right, so here, this is supposed to have a limit. as x approaches infinity. All right, so this is the limit as x approaches infinity of the first one. Okay, now they're being multiplied, right? So times the limit as x approaches infinity of the second one. And we're going to do them as two mini problems in one. All right? So, let's look at the first one, and let's just go slow. So take a look at this, the 1 over x. Okay, what happens as x approaches infinity? It's going to be 0. Plus, what about that one? That's just the 1. Okay, so that's the first one. Now, times, let's take a look at the next one. It's going to be 4x squared over x squared. So that's just 4, not 4 minus 1. So here's why it's different. This one, it's the entire numerator over the denominator. So you just take the highest term from the numerator. Here, they were two separate entities. Okay, this was not a common denominator. That's why we did them separately. Yes?
Wait, we did the. Why did we do minus 1?
No, because this was the entire numerator over the denominator, so we just take the highest term. Whereas here, there were two separate entities. It was not a common denominator. Okay? You can make it a common denominator, and then it'll still be a 1, right? Because it would be x plus 1 over x. And it would just be a 1. It would be more work. Okay. So now, so that was limits as x approaches infinity. Now let's talk about when x approaches a constant again, if you have infinite limits. So let's talk about this. If when x approaches a number, the function goes up to positive infinity or down to negative infinity, we say the limit of f of x as x approaches a is infinity or negative infinity. And we can also say it does not exist dn. Remember we were talking about this yesterday or the day before on Monday when we were talking about these, right? So it's more of that we're going to do. Okay, so let's use graphs to find the limits of these.